Um, Good afternoon. Welcome to today's distinguished colloquium. Our speaker is Umesh Vazirani from UC Berkeley. He's Roger Strauch Distinguished Professor in Electrical Engineering and Computer Science at UC Berkeley. Among his honors are the Friedman Mathematics Prize, the Fulkerson Prize from the Math Programming Society and the American Mathematical Society, Vannevar Bush Faculty Fellowship, Miller Research Professorship, and member of National Academy of Sciences. Umesh is truly one of the founders of quantum computing, and he got on this track in the early 1990s as a junior faculty member at Berkeley, and wrote some of the foundational papers that laid the foundations for this field, including what is a quantum computer, when is it useful, and the notion of quantum supremacy, that quantum computers can be exponentially more powerful than classical computers. Over the years, as quantum computing became real and quantum devices started being manufactured, Umesh came up with interesting theory about testing and using them for various purposes. And along the way, his work has had profound implications for quantum mechanics, the reality of quantum mechanics and what it really implies for physics. And maybe his talk will touch upon those as well. So today he'll tell us about theoretical reflections on quantum supremacy. And just a word about questions. You're welcome to enter your questions into the chat box and I'll monitor them, and Umesh will periodically pause and answer the questions. So take it away, Umesh.
Great. Yeah, thanks a lot, Sanjeev, for the very nice introduction, and really a pleasure to visit. Even though it's over Zoom. So I'm sure you saw announcements like this about Google's quantum supremacy experiment of a year and a half or so ago. But you know, and there are a lot of questions about this experiment, including how much of it is hype and what aspects of it were really interesting, what were the advances, and what does it tell us about the future. So in this talk, I'll try to talk about all these issues, as well as, you know, how the subject has been shaping up. So to begin with, let me just say, you know, at a bird's eye view, what one can say is that Google's experiment was really quite an advance in terms of quantum computing hardware. So the fact that they were able to get 52-qubit quantum circuits of depth about 20, but more importantly, with a gate fidelity of about 0.99, so an error rate of under 1%. You know, this was quite an achievement experimentally. I think it's also fair to say that even though this was a great achievement experimentally, you know, that it would not have garnered quite this widespread attention that it did without a second aspect of it, which was this claim of having achieved quantum supremacy. And this took a lot of doing, you know, and there was a lot of theoretical work that went into justifying that this experiment plausibly achieves quantum supremacy, you know, where plausibly needs to be emphasized, because in a sense that I'll make clear. Okay, so what is quantum supremacy, first of all? Well, quantum supremacy in computer science terms is a violation of the extended Church-Turing thesis. You know, so the term itself was coined by John Preskow, and it's a much more, you know, it rolls off the tongue much better. But the extended Church-Turing thesis, obviously, you know, which is how we think about it in computer science, is you know, it says that any reasonable model of computation can be simulated on the most basic one, the Turing machine, or probabilistic Turing machine, with at most a polynomial time simulation overhead. And if you want to think about where this thesis comes from, there's a logic, sort of way of looking at it, and then there's a physics way of looking at it. But if you look at it from the physics viewpoint, then it basically says, look, anything that you describe in physics, in classical physics, can be written in terms of local differential equations. And if you discretize it, you would get the dynamics being described by a cellular automaton. And cellular automata satisfy the extended chain-sharing thesis, and therefore, that would be a proof that that this is the ultimate model. Now, back in the early 90s, 91, I think I came across Feynman's paper from a decade before, simulating physics on a computer. And to my reading, it seemed to be saying quantum mechanics breaks this, quantum mechanics should challenge this thesis. And so, I ended up studying up on quantum mechanics as a result. And then, what we showed was, together with my student Ethan Bernstein, was that in fact you could show something formally that quantum computers are programmable, that they are digital with respect to inverse polynomial errors, and that for certain completely useless benchmarks, a challenge problem, you can get super polynomial speedups. Now, what happened after that is that in each of these three regimes, things got over the next few years improved considerably. So, dramatically. So, for example, the following year, Peter Shor showed that, in fact, you can get practical speedups of exponential speedups for really important problems like factoring and discrete log. The robustness with respect to errors was improved to constant through this work on fault-tolerant quantum computation. And the programmability was greatly improved by a different model where you can think of a quantum computer as a classically controlled quantum register. And so now that we are, in a sense, we are back to this very early kind of violation of the extended chain-sharing thesis, now from an experimental viewpoint. So again, where the robustness is with respect to 1 in poly errors, and we are back to sort of saying, is there a challenge problem on which quantum computers can do better in practice? Okay, so now let me sort of back up and say something about quantum computation. So, I'm sure you know that the place where the quantum speedup comes from, the initial impetus from it comes from the fact that if you are trying to describe the state of n qubit system, then you need 2 to the n complex numbers, because you get a superposition over all possible 2 to the n n-bit strings. Now, there's a theorem which says that, in fact, if you measure the state, no matter how sophisticated your measurement is, you can get at most n classical bits of information about the state. And so, up to this small number of classical bits leaking out, we really can think of this quantum computer as a black box. Okay? And so, you might think that there's no way that that nature sort of keeps us from probing this exponential nature of Hilbert space. But even back in the day, we realized that one of the consequences of this computational viewpoint on quantum computers, or in terms of quantum mechanics, was that even though a naive reading of the axioms of quantum mechanics would say that we can never know that there's an exponentially large Hilbert space, if you actually do an experiment demonstrating this exponential speedup, then this would give you somehow a handle into Hilbert space that we could not get otherwise. Now, okay, so how should we actually do such an experiment? So the obvious way to do it is to use Shor's quantum factoring algorithm. So what you would do is pick two primes P and Q, multiply them to get n, and then ask the quantum computer to factor n. Unfortunately, that day is quite far into the future, where our quantum computers would be powerful enough to do that. And this sentiment was captured really nicely by Aronson and Archipov, where they said, well, shouldn't you be using quantum computers to do something that's native to them? In much the same way that if you were testing a dolphin's intelligence, you wouldn't really ask it to solve arithmetic problems. And so, this triggered a long sequence of theoretical works on quantum supremacy about a decade ago, starting with this paper of Aronson and Archipov. Now, let me just briefly describe what the Gould experiment is, because it wasn't one of the theoretically inspired experiments originally, in its conception. And so it took a lot of post-facto theoretical analysis to say, is this really a well-formed experiment? But the experiment is this. So, it's around a 52 qubit chip, a superconducting chip, which, this is an illustration where these crosses are the qubits, and these rectangles are the adjustable couplers, which apply the gates. Now, 52 qubits means you're probing a 2 to the 52 dimensional Hilbert space. And, this number is large enough so that it's impressive, but it's small enough that you can plausibly do supercomputer simulations. And so that's going to play a big role in this particular experiment. And so the way you set things up is you think of a random quantum circuit of depth 20, okay, and that's what you're going to fix for the course of this experiment. And now you initialize each of the qubits to the 0 state. You run the quantum circuit, and you measure the output. Now, when you measure the output, you're going to actually get a sample from some probability distribution, which is the output distribution of this circuit. And so you get some sample string X, which is 52-bit long, sampled according to some distribution P sub C of X. And now you want to check whether these X's that you sampled actually came from this circuit, quantum circuit C, that you were expecting to sample from. And so this is where there's a measure that was used, which is called the linear cross entropy, which is you compute the expected value of P sub C of X. So how do you do, first of all, how do you do this? And secondly, why should this be a good measure? So the way you do this is you pick a large number of samples. You run your quantum computer many times to generate a lot of samples. For each one, you compute P sub C of X on your classical supercomputer. And now you figure out the sample average of these P sub C of X's. And now, what are you looking for here? So the intuition is that whatever your output probability is, your higher probability X's will show up more often. So when you look at the expected value of P sub C of X, it'll tend to be large depending upon the distribution. So how large should it be? So let's start with as a reference point. If the circuit C outputs uniformly random strings, then no matter which string it outputs, its probability would be 1 over 2 to the n. So therefore, the expected value over X of P sub C of X would still be 1 over 2 to the n. For a random quantum circuit, this expected value should be twice as large. That's because it follows some sort of a Poisson distribution. Okay, and so well, what happened Google did their experiment, they got a value which was 1.002 divided by 2 to the n. And they wanted to conclude from that this showed plausibly that they had achieved quantum supremacy. So now, as you can, as you might imagine, this raises various questions. Which is, how do we know that random quantum circuit sampling is hard for classical computers? Right? How do we know that behind the scenes, whatever they had implemented wasn't actually, didn't actually behave classically, even unknown to them? And second, even if it's a hard problem, how do we know that the Google machine actually succeeded in sampling from the output of this particular random quantum circuit? So how good was this test? Okay, so there are three kinds of evidence one can give, in support of these claims of quantum supremacy. I'll outline them from going from the most formal to the least formal evidence, and actually also from the least convincing to the most convincing. So the most formal will be the least convincing, I think. So the first kind of evidence comes from complexity theory, and it says, well, look, probability distributions that are generated by quantum circuits look very different from those generated by classical circuits. So in what sense? So basically, when you have a quantum computer working, you have constructive and destructive interference along exponentially many paths, which, there are many ways to get to the same output string X. And, all the ways of getting there give you amplitudes which are positive or negative, and they can cancel, and the eventual probability is the square of the amplitude, total amplitude of getting there. One consequence of this is that if you have a classical probabilistic circuit, if you want to compute what's the probability that this circuit outputs X, this would be in the complexity class sharp P, whereas it's just counting, and whereas for a quantum circuit, it's in gap P. It's the difference of, you want to compute the difference between two probabilities, two numbers, okay? And the point is that even approximating a gap P function can be sharp P hard, and therefore it lies outside the polynomial hierarchy. So this is the main idea behind this complexity theoretic approach to justifying quantum supremacy. And so what you have to end up doing is doing what's called a average, worst case to average case reduction, and these tend to be quite delicate. So I'll just give you an approximate, sort of very approximate statement of a theorem that we showed, which says that if a polynomial time classical circuit can output from a distribution extremely close to the output distribution of a random quantum circuit, then the polynomial hierarchy collapses. Now, as it stands, this doesn't have much, you have to be very, very close to the output distribution, and that's not something that the Google experiment obviously achieves. So a second kind of evidence that you could give is this sort of heavy output generation hypothesis. This was done by Aronson and Chen, and then the particular one I'm going to talk about is due to Aronson and Gunn. Sam Gunn was an undergrad when he did this at Austin, and he's now a grad student with me. So how does this work? It's sort of what they put forth is a hypothesis. And if this hypothesis is true, then they can justify the supremacy claim. So what's the hypothesis? So the hypothesis says that, let's look at the output of this random quantum circuit, and X, let's look at any X. And we want to know, given an X, is it, guess with probability at least half plus some exponentially small amount, whether the probability that X would be output by C is higher than the median probability or lower than the median probability. In other words, if I give you an X uniformly at random, can you guess which side of the median it lies? And this is going to be, this is, the hypothesis is, this is, this is, this is really, it's really hard to get even an inverse exponential advantage in the number of gates. And if you assume this hypothesis, then you can basically show that even if you output, produce the output of the quantum circuit with probability exponentially small in m, then you've demonstrated quantum supremacy. So, one way to think about this hypothesis is it's in the style of the exponential time hypothesis. You assume something pretty strong about about satisfiability, and you get various consequences. So the nice thing here is that there's a very well-defined hypothesis. It's a pretty bold hypothesis because if you use the Feynman path integral sort of approach, you can already get half plus an exponential chance of telling whether you're above or below the median for some constant b, but not but it's a larger constant. Okay, so the third way you can approach this is by a back of the envelope calculation. You can say, well, look, the fidelity was 0.99, meaning the error per gate is about 1 in 100. The number of gates was 50 times 2, which is about 1,000. So if you compute it, the probability that you expect no error is about 1 in 1,000. And now if you put forth a hypothesis saying the output distribution behaves like a convex combination of the correct output distribution and something that's completely uncorrelated with it. Let's think of it as a uniform distribution. So now by collecting enough samples, you will see the signal, you'll see this true distribution. And the number of samples you'd have to collect may be roughly 1 million, and that's what they actually end up doing. Okay, so that's this plausibility argument that quantum supremacy was achieved. So now, one can argue that quantum supremacy is not a one and done experiment. It's really an important scientific experiment. And the sense in which it's an important scientific experiment is that, you always want to test physics in the limits, of very high energy or very small sizes or very large velocities. And every time physics is tested in a new limit, something interesting happens. So now if we were to say, well, this exponential growth of Hilbert space, this is, this exponential computing power is arguably a very counterintuitive aspect of quantum mechanics. So, we should be testing physics in this new limit of high complexity. And so that's what a quantum supremacy experiment is. And so, if you look at how the Bell tests have been done over the last more than 50 years, they've been refined repeatedly to eliminate various loopholes until very recently we got to these loophole-free Bell tests. So in a sense, the same thing I think will happen with these quantum supremacy experiments, where they'll improve over time, both in terms of the hardware, but also in terms of our justification of them. Now, it's already the case, a few months ago, there was a claim from China about boson sampling experiment that beat Google's experiment. This was by Zhai Pan and Xiaoyang Lu. Essentially, they were, you could think of them as doing this experiment on 76 qubits. Unfortunately, their verification, is not quite as convincing. So instead of sort of being able to say, look, we achieved quantum supremacy, what they end up saying is they can distinguish the output distribution of their setup from 3 reference classical distributions. So you could sort of say, well, why did they not get the stronger conclusion? And in a certain sense, there was this, if you look at it in terms of this heavy output generation hypothesis, in the case of boson sampling, this hypothesis, this very strong hypothesis breaks down, that you cannot guess whether output string is above or below median probability. And so this is what leads to, is at the basis of the fact that you cannot quite get that. Okay, so let me just discuss this first, wrap up this first part and then move on. So one of the things that comes up through these quantum supremacy experiments is that they are a very good source of benchmarking. So, in benchmarking, when you want to know how well you could benchmark individual gates, but one of the things that you run into is noise like crosstalk, where as you increase the number of qubits, it's very hard to calibrate and see what the noise process actually looks like. And so you can use this sort of a quantum supremacy experiment as actually a benchmarking experiment. And then once you look into the box, you can actually work through ways in which random circuit sampling and everything we know about it can be used to do benchmarking as well. The second thing I'd like to say is that beyond this, seeing it as a great experiment, it's also a milestone on the way to getting a working quantum computer. And so it's really important to scale this beyond this Goldilocks limit, of 50, 70 qubits, where you can do classical simulations effectively. And so one of the things you want is that you want to be able to set up experiments where the classical computation needed for verification is small. Currently it far exceeds the classical resources required to solve the original problem. So maybe the next milestone is actually getting rid of this problem. And then a third thing is that we really need some sort of a scheme where there's a rigorous proof of quantumness. Okay, so so before I move on with the talk, let me just check if there's anyone who has a question.
Yeah, no questions as far as I can see. So
okay.
I guess your talk was very clear.
Okay, great. So let me just say, please do ask questions if you feel up to it. And okay, so in the meantime, let me just proceed. So okay, so now, what's the problem once we go beyond this Goldilocks limit? So there are two basic problems. One is, the problem that I already discussed, which is a quantum computer really behaves like a black box for all practical purposes, right? You get to see only a small amount of information from this quantum computer about its inner workings. And the second thing is that it's also a very powerful computer in general. So how do you, and that's the real reason we want to be running it. So those are the aspects of it we'd like to actually invoke. And so how do we get from this picture, to the picture where we are at this below this Goldilocks limit? And so here's an idea. So quantum computers aren't all powerful, in the sense that there is such a thing as post-quantum cryptography, which is that there are classical crypto systems, which you can implement, where encryption and decryption are both done by classically. But on the other hand, even quantum computers, we believe, won't be able to break them. Okay, so and so, for example, if you have such a public key post-quantum crypto system, then if you have the trapdoor information, the secret key, then you can decrypt a message which even a quantum computer wouldn't be able to do. Okay, so how should we use this this ability to level the playing field? So there are two ways you might want to do it. One way, which is the wrong way, is to force the quantum computer to play on the classical verifier's turf, thereby completely crippling it. That would be, it would not be very useful. So the right way is that you want to make it play on turf where the classical computer, the classical verifier, has an advantage and can check. But it still allows the quantum computer to do the kinds of quantum steps that make it powerful, right? And so this is something that we implemented in this form of a qubit verification protocol with Zvika Prekursky and some of my students, Paul Cristiano, Urmila Mahadev, and Thomas Vidic. So what this involves is, it's a very simple protocol where the classical verifier interacts with the quantum computer. And at the end of this protocol, the quantum computer holds a qubit, which is either in the state equal superposition of 0 and 1, or that superposition with a minus sign, so 0 minus 1, with a phase of -1. And whether the phase is +1 or -1 is determined by some bit b, and the quantum computer knows the classical the encryption of b in some post-quantum cryptography, right? So the quantum computer cannot figure out what the phase is. The quantum computer can send this information to the classical computer, who know then what this qubit is. And so now you have these two different capabilities. From the point of view of the quantum computer, getting a 50-50 bit qubit in one of these two states, it turns out this is completely indistinguishable from a completely random qubit. And so the quantum computer can create this qubit, it can manipulate this qubit, but it has no idea what this qubit is. Meanwhile, the classical computer cannot manipulate any of this information, but knows what the state of this qubit is. Okay, so
Umesh?
Yes.
I think I could use another run through of who controls what in this picture.
Okay, so in this picture, the verifier is classical. Okay, the interaction between the verifier and the quantum computer is all classical. Right. So they carry out a conversation, and I'll show you what that conversation is in a couple of slides. At the end of that conversation, the quantum computer has this qubit, which is either 1/√0 plus 1/√1, or 1/√0 minus 1/√1. It's a single qubit, which is in a superposition of 0 and 1. And which of these two is chosen at random? In the course of this communication, also the verifier ends up with the encryption of b, the bit b, and so the classical verifier knows whether this qubit was in the plus state or in the minus state. Okay. All right. Now, here's another fact. If you have a qubit which is 50 with probability half in this plus state and probability half in the minus state, that's completely indistinguishable from a qubit which is in the state 0 with probability half and the state 1 with probability half. So it's a completely random qubit. So from the point of view of the quantum computer, it has absolutely no idea what it's dealing with. And from the point of view of the verifier, it knows what the quantum computer has. And, but obviously it cannot control it directly.
And this is using some cryptography that's believed to be quantum resistant?
Yes, I'll show you that in a moment. Okay, so the particular crypto primitive that we use is what's called a trapdoor-claw-free function. So for our purposes, it's think of it as a function that maps n-bit strings to n-bit strings. It's a 2-to-1 function, right? So if f of x naught equal to y, then there's also an x1 which maps to y. So this function is, we'll assume it's easy to evaluate. It's hard to invert. It's in fact hard to find any claw. So it's hard to find x naught, x1, and y for any such triple. Okay. Now there's a implementation of these based on LWE, learning with errors, which is sort of a leading candidate for post-quantum crypto. And learning with errors just says say you're working mod Q, you're given a matrix A, and so you're given a bunch of linear equations. So you're given Y and a matrix A, and you want to figure out what S is. So this is the secret. So this would be a trivial problem, except that we've added in a small amount of noise in each of these equations. And the number of equations is much larger than the number of unknowns, so that S is uniquely determined by these equations. But of course, in the presence of noise, you can't use Gaussian elimination or any of the standard algorithms. Okay, so this trapdoor claw-free function is just built up out of one such LWE sample. So you're given Y, you're given one such. Sorry, I used the same Y. Let's call this something else. U is this LWE sample. So you're given one such LWE sample U, and based on that, you can define your claw-free function. And then if you can break the claw-free function, then you can figure out S. That's the guarantee. Okay, so now let me just give you an outline of the protocol. So the protocol is like this. So the verifier sends to the quantum computer F, or in this case, the LWE sample. The quantum computer returns a random Y. This is in the image of the 2-to-1 functions. Then the verifier issues a challenge, 0 or 1. 0 says, give me a pre-image. So if it's a pre-image, then the verifier sends back either x0 or x1, which maps to y. Or if it's 1, then that's an equation test. So the quantum computer must respond with some equation D, which connects x0 and x1. So now there are two properties of this protocol. One is that the quantum computer can efficiently answer either challenge. Okay. The second property is that no polynomial time classical or quantum computer can answer both challenges. So if you ever answer both challenges, then you can break the crypto system. So now I want to claim from this that no classical computer can possibly answer either challenge. Now, this may seem paradoxical because what I'm basing it on, this second statement, is symmetrical in classical and quantum. It's saying neither of them is able to answer both challenges. But the point is that a quantum computer can answer either challenge without answering both, whereas a classical computer cannot. You see, if a classical computer was willing to answer either challenge, then what we could do is we'll go through the steps of the protocol, issue a challenge 0, get back a pre-image, and then what we can do is rewind the classical computer back to its state right after it sent us Y. And now this time we'll send it the challenge 1. And now it'll send us back an equation. So because, so you can say it in one of several ways. Classical programs have traces. You can look at what they were doing. Quantum do not. Quantum systems, they don't have trajectories. You set it up and then later you measure, but you cannot say how did you get from A to B in in the classical case, you do have trajectories. So this is really what we are using. Okay, so now let me just describe this just a little bit more, and then so what can you do quantumly? So for those of you who know, what you can do is something like what you do in Simon's algorithm. So what we do is we set up a superposition on all x's, we compute f of x, we measure f of x. So that gives us a random sample y, which is in the image of f. And then we'll be left with our input register in a superposition over the two pre-images. So we'll be left with an equal superposition of x0 and x1, the two pre-images of y. At this point, if we are given the 0 challenge to find a pre-image, we could just measure to get either x0 or x1 with probability half. Okay? So by the way, this is not something really remarkable at all, because since you're getting a random pre-image, you could have got the same thing by just picking a random x, computing f of x, calling f of x equal to y, and then the x you started off with is either x0 or x1 with probability half. So there's nothing great about this so far. So what quantum mechanics gives us is a way to measure in a different basis. And so what we can do is measure this register in the Fourier basis, or do Fourier sampling. And what you end up with then is an n-bit string D, such that D inner product with x0 plus x1 is 0. So here the addition is bitwise mod 2. Okay, so it basically gives you one linear equation about x0 plus x1. Okay, so now this is how a quantum computer would actually run this protocol. So now, why is it that a classical computer cannot do this? Okay, so here's how we have to argue. So for a classical computer to succeed, it must provide both, right? It must, with significant probability, it provides both a pre-image as well as an equation, right? As well as some D such that D inner product with x0 plus x1 equal to 0. Okay, so now what we want to claim is that you cannot do this without breaking the crypto system. But breaking the crypto systems means finding x0 and x1 and y, finding a claw. But here we only found x0 and a bit of information about x0 plus x1. Moreover, this bit of information is something that the adversary chose for us. Okay, so now to show that this is really hard, we have to show that there's a very strong hardcore bit property. It's a new kind of, we call it the adaptive hardcore bit. So basically it says, if you base this trapdoor claw free function on LWE, then, and if you happen to know one of the pre-images x, so if you're given y and you know one of the pre-images x, and if you have a better than 50-50 guess for this bit D time inner product x0 plus x1 for any choice of D. So, the adversary can choose D. Then you get an efficient algorithm to break LWE. Okay, so now the reason we can do this is that there's this technique that's been developed for LWE cryptography, which is really very beautiful, very strong technique called leakage resilience. And that allows people to prove very interesting hardcore bit properties, much more powerful than before. And then we just get to soup it up a little bit more to get this property. Oops. Okay, so sorry, let me just see if there's any questions. Otherwise, I'll sort of develop this a little bit further.
No questions.
Okay, great. So now let me say how one can use this primitive to go a little bit further. So towards generating what's called certifiable random numbers. Okay. So what does it mean to certify random numbers? So let's say we have a quantum device. We think of it as a black box. we think of it as an untrusted black box. What it's supposed to be doing, if it's operating correctly, then if we feed in log n random bits, it outputs n random bits. Now, for a quantum computer to output random bits is not a big deal, right? You could just put a qubit in a state equal superposition of 0 and 1, measure it, and you will get a random bit. The thing that we want here, which is different, is we don't trust this box, either because we don't trust that it's well calibrated, or we think it's actually adversarial. And we want to be able to certify not that it's working correctly on average or something like that. We want to certify that this particular n-bit string must be random. And it's a really sort of strange thing, but this is something that you can do with quantum mechanics. And it's something that would be completely, it's clearly impossible in a classical world. And so how do we do this? So let's go back to the same protocol that we had. Now we choose F pseudorandom, LW sample pseudorandomly. So we use only log n bits to pick F. We have the quantum computer, sort of commit to Y. We use, and now we use a sequence of such things where we use a few one challenges to make sure that the computer is being honest. And we use the 0 challenges to generate randomness. And if you write out this protocol, then it turns out we can show that as long as this quantum computer is unable to break the cryptography during the protocol, then this output is actually going to be statistically random. It's not just pseudo-random. And so how do we actually show that it must be statistically random? So for this, we have to reach into the device, and we have to say, well, the internal state of the device must effectively be a qubit in the state 1 over square root 2, 0 plus 1 over square root 2, 1. Okay. So and then it must be measuring it in the standard basis if the challenge is 0. So in that case, you get with 50-50 probability 0 and 1. In the Hadamard basis, if the challenge is 1, in which case, when you measure it in the Hadamard basis, you always see 0, which is what you get an equation with a 0 here. So that's what we want to say, that effectively that's what's going on behind the scenes in this black box. And so, this is this general idea that you can sit outside and you can classically know what's going on inside this Hilbert space. So, and the idea behind this is, okay, so I'll just say something for a couple of minutes for those who have a little bit of background in quantum computing. So a qubit is basically defined by 2 anti-commuting measurements, an X and Z measurement. Okay. In this case, we have these 2 measurements. Is the equation 0 or 1? Is the pre-image X0 or X1? Now, this hardcore bit property that I just spoke about says that these 2 measurements are almost perfectly uncorrelated, which means that they are, okay. So now, which means that this measurement angle is almost exactly 45 degrees if you were restricted to a 2-dimensional space. So what we do is we take the Hilbert space of the device and use Jordan's lemma to decompose the Hilbert space as a direct sum of 2-dimensional subspaces. And now we invoke this hardcore bit property to say, in most of these 2-dimensional subspaces, the angle must be very close to 45 degrees. And so up to errors. And so then we correct and we get a small error, but now all these angles are 45. And so by aligning them, reconstructing it, we get a qubit. And so what we are basically saying is up to a unitary change of basis, we must have had a qubit. This actually shows up in a number of other places. In fact, this sort of reaching into the Hilbert space of these black boxes was sort of the central theme in these papers on either verifying quantum computation when you have two entangled quantum computers, or in terms of doing quantum cryptography, where where you don't trust the quantum devices that you're using. Okay, so I should say that that this basic protocol that I showed you, it can be used to create to solve two very beautiful problems. One is quantum fully homomorphic encryption. This is where you want to delegate your quantum computation to the cloud, but you don't want the privacy of your data to be compromised. And so, this problem was completely solved by an extension of this protocol, and as was if you want to verify a quantum computation now in this cryptographic setting. You want to verify that what the quantum computer outputs on a given input is actually what it should be outputting. So both of these were done by my student Urmila Mahadev. They're actually very nice quanta algorithms, quanta articles that describe some of these at a high level. I should. How am I doing on time? Is it?
Maybe another 2-3 minutes.
Okay, let me skip ahead a little bit. So the whole point of this was that actually, if you want to do quantum verification, then there's a simplification due to Georgiou and Vidic, which sort of says once you do this this sort of qubit preparation protocol, right? That if you generalize it slightly, instead of a phase of plus or minus, you have the 8th roots of unity. Then you can use it in a much simpler way to do verification. Let me just say one more thing, which is there's a way you can do this proof of quantumness without going through adaptive hardcore bits. This very strong property that we have, and the point of this is that once you don't need the adaptive hardcore bit property, then you can use various other trapdoor claw-free functions, including x squared mod n, for doing, as long as you want to do it for proofs of quantumness. So you don't even have to use post-quantum cryptography. And what's interesting here is that to make this happen, we have to use a modification of the basic protocol to incorporate this CHSH game. This is the game, the Bell test, which happens when in this setting where you have two entangled quantum computers. So here in this setting, we don't have two entangled quantum computers. We have a classical verifier and a quantum computer interacting with each other. And so what you do is you use the computational hardness from the crypto problem to essentially replicate this space-like separation we had between the two quantum devices in the Bell type in the Bell type setting. And so okay, so that gives us this way of using much simpler trapdoor claw-free functions. There's also something else we can do, which is we can, in order to actually run a quantum computation, you have to make sure it's reversible. So you always have the problem of having to uncompute whenever you want to discard garbage bits. So in this particular case, we actually show that you can actually discard garbage bits without uncomputing, and so that speeds things up quite a bit. So there's there's a group that's just finishing up a proof of concept implementation of all this on ion trap quantum computers. Okay, so let me just wind up here. So just a few things. First, you know, quantum supremacy is not a one and done experiment. I think we are going to see more and more convincing versions of this experiment done over time. In particular, I think we'll also see scalable versions of it. One thing that this experiment demonstrated is this. I think what will be what I expect to be a model for some of the most interesting experiments that will be done moving forward, which is that there's going to be some computational principle that's going to be illustrated by the most interesting experiments, and it'll take a very robust theory experiment collaboration to put these together in much the same way as this quantum supremacy experiment did. The second point has to do with benchmarking and to what extent we can analyze a quantum computation. So the point is that quantum algorithms are not at all like classical algorithms, right? Quantum computations look very different. So because quantum mechanics seems to want to hide its tracks, so there's no such notion of a trajectory. And so you don't have the trace of a program to work through to see what happened. And so I think that, it's for these reasons that we'll need these completely new techniques to look into what actually happened during a computation. And then, these techniques will also come in terms of benchmarking and understanding what the quantum computers are capable of as a way to refining them further. It reminds me that, when I was in my early days as an assistant professor, one of my computer architecture colleagues once said to me, the most important application of computers is designing better computers. And that was may have been true back in the day for classical computers, but it's definitely going to be the case moving forward for quantum computers. My last point is that, if you were to do a naive reading of the axioms of quantum mechanics, they would seem to rule out ways of probing Hilbert space, and in these interesting ways, in terms of showing that the Hilbert space is exponentially large, or reaching into it in the ways that we saw. And yet, once you use computation, you can reach in ways that seem paradoxical if you just do a naive reading. And so, on the other hand, all the examples that I gave you were very computational in nature. And so, one can ask, if you think from a physics viewpoint, now that we know that we can reach in these ways, are there physics applications of this that you wouldn't even have thought about otherwise? Are there things that you can do, physically once you say that, well, you have computational access to Hilbert space, so you have a classical computer reaching in through these techniques. Is there some way to do something that we didn't even dream of before? So I'll leave it at that. Thank you.
Thank you, Umesh, for that fascinating talk. There's one question in the chat. It's a long one, so you should probably read it. And others should also feel free to ask questions. Do you see it, Umesh?
Oh, sorry. Sorry. I thought. Okay. Let me just.
So I'll read it out to you. It's Chipeng Liu. He says, or she, I'm not sure. Is there any reason to use 2-to-1 trapdoor functions? Is it because any x0, x1 form an affine space, and doing QFT over that forms an equal superposition over another space?
I see. So, yeah, I think, yeah, sorry, by the way, for some reason, I'm not able to read the Q&As. They don't show up.
Okay.
But,
So that was the question. Yeah.
yeah. Okay. So yeah. In answer to the question, yeah, you know, the reason we use the 2-to-1 function is well, it's somewhat along the lines of what you're saying. So basically, what we are doing via the 2-to-1 function is we are setting up a superposition, right? So because it's 2-to-1, once you compute f of, once you know that f of x equal to y, you know that there are two preimages, and so there's a superposition of two things, right? And that's a qubit, right? So, but it's a qubit in a basis that the quantum computer doesn't know, because it doesn't know x0 and x1. And so the fact that it doesn't know what x0 and x1 are, on the one hand, it ties its hands in terms of what it can do, in terms of what it knows about that qubit. On the other hand, it leaves it in a form where, it leaves it in a form where, where it can be manipulated. And so that's the reason for the 2-to-1 function. I hope that's.
Yeah, there's another question from Mark Braverman, but I see that you're meeting him later, so maybe you can discuss that there. So my other question, last question for you was, what are some of the other areas in where quantum computing and these ideas are impacting physics?
Oh, I
either
see.
Experimental or theory.
Well, there are, so there are a number of things where ideas from quantum computing are impacting physics. So, for example, there's the notion of pseudo-random quantum states, right? So you can say a particular quantum state is pseudo-random. It cannot be distinguished from a random state. And then this turns out to have some implications for, this ADS-CFT duality, which comes up in quantum gravity. Then, of course, there's all these implications of quantum error correcting codes to quantum gravity, and actually to the foundations of quantum gravity. There are these connections between. So I'm interpreting your question much more broadly, not just the particular ideas I spoke about, but if you want me to limit it to these, do you want to?
No, that's fine.
Yeah.
Well, there's one final question from an anonymous attendee. Is quantum supremacy necessary, crucial for practical applications of quantum computers? Or is there just a potential for them to become useful, kind of like GPUs?
For quantum computers to become useful accelerators like GPUs?
Yes.
Well,
which is not exponential speed.
Yeah, I think that there's a calculation you can do which says that you really do need. Okay, so no matter what, you're going to need an acceleration, but in fact, for the foreseeable future, the individual steps of a quantum computer are going to be slower than that of a classical computer. And so you're going to have some algorithmic speed up in order to get an overall gain. And so I think that maybe as a mathematical statement, one would say, no, it's not necessary. But as a practical statement, one would have to say, yes, it is necessary.
Okay, thank you very much. Maybe we'll end the seminar here, so you have a break in your schedule. Thanks again, Umesh.
Great.
And I'm sure the audience really like this big picture talk. Thank you.
Great, thanks.